this lecture, we'll discuss about the Cauchy-Schwarz inequality, which states that for all vectors x and y in n-dimensional space Rn, the inner product of x and y is less than or equal to the product of their norms. And here we are going to prove it in a little bit tricky and geometric way, rather than explicit mathematical expressions and calculations. The Cauchy-Schwarz inequality plays a crucial role in proving the triangle inequality for n-dimensional Euclidean space for all natural numbers n. Now we know three properties of inner product, and those are: it is positive definite, symmetric, and bilinear. And we will use all these properties of inner product to prove the Cauchy-Schwarz inequality. So first, let us consider a vector x in two-dimensional space, and then again consider the vector y in that space. Now since a vector only has magnitude and direction but no position, we just can displace it without loss of any generality. And for this case, the resultant vector represents the vector x plus y. And let us represent the vector x plus y as w. Also we can represent w as x plus unit times y, where unit 1 is a scalar, which scales the vector y. Now instead of 1, if we choose different values of the scalar, then w will represent different vectors. So for any vector x and y in R2, as well as in Rn, for all n in the set of all natural numbers, we always can construct a new vector w is equal to x plus ty, where t is a variable scalar. That is, if we change the scalar t, then the vector w will be different. Now for any arbitrary t, if we consider the inner product of w with itself, then we will simply get square of the norm of w, which is in fact a scalar. And here in particular it is a real number. And we know that square of norm of w is non-negative, which actually is from the positive definiteness of inner product. Since w varies for different values of t, therefore norm of w depends as well as varies on the value of t. That's why we can consider the square of the norm of w to be real valued function of t, and let it be f of t. So ft is an inner product of x plus ty with itself and is non-negative. Now using the symmetric and bilinear property of the inner product, we can simplify the above expression of ft, where all these inner products are scalars. Now if we represent them as c, b and a respectively, then the equation reduced to c plus bt plus at square, which is a non-negative quadratic polynomial of degree 2. Now by fundamental theorem of algebra, a polynomial of degree 2 can have at most 2 roots. But when ft is greater than 0, then obviously there will be no such root of f, and that implies ft is not equal to 0 for all t. Now ft is equal to 0 implies c plus bt plus at square is 0. And from here, by Sridharacharya's theorem, we get t is equal to minus b plus minus a square root of b square minus 4ac by 2a, where t is the value for which f is 0, that is t is a root of ft. Also, you can realize that the nature of the roots is dependent and determined by the discriminant of the polynomial, which is b square minus 4ac here. And the roots of the polynomial are related with the discriminant by this equation. T is equal to minus b plus minus square root of b square minus 4ac by 2a. Now here in this particular case, f t is greater than 0. That is, f doesn't have any real root. And obviously, that can only happen when b square minus 4ac is less than 0, which eventually gives the square root of b square minus 4ac is in the set of all non-real complex numbers. That's why, in this case, t is not a real number. That is, the polynomial will not have any such real roots. Lastly, since this plotted quadratic polynomial ft is greater than 0 for all t, therefore b square minus 4ac is less than 0. Now if we consider b square minus 4ac is equal to 0, then we will have t is equal to minus b by 2a. And since a quadratic polynomial either has no root or has two roots, therefore t is equal to minus b by 2a becomes its double root. And the quadratic polynomial for this case will just touch the t-axis, having its double root on that point. So this condition will take place when f is non-negative, f has a double root, and its discriminant is 0. Lastly, if we consider b square minus 4ac to be greater than 0, then t has two different real values. That is, f has two different real roots. On top of that, those two real roots are conjugate to each other. And you can simply check, in between those two real roots, f has a negative value. That is, for some real number t in between those two real roots, ft is negative. So long story short, here f has both positive and negative value and has two different real roots. And the discriminant of f is positive also. But we know that in our case, ft must have to be non-negative. That is, ft is greater than or equal to 0 for all t in the set of all real numbers R, the scalar field. And this condition forces us to conclude that the discriminant must have to be non-positive. That is, b square minus 4ac is less than or equal to 0. And from this one, we can conclude 2 times inner product of x and y and its square minus 4 times inner product of x with itself times inner product of y with itself is less than or equal to 0. And gradually this implies inner product of x and y and its square is less than or equal to norm x square times norm y square. And we can simplify the right hand side by considering as norm x times norm y and its square, where norm x times norm y is non-negative. And that's why we can conclude inner product of x and y is less than or equal to norm x times norm y for all x and y in the n space Rn. And this is the Cauchy-Schwarz inequality. And using this Cauchy-Schwarz inequality, we can simply prove the triangle inequality for vectors in n-dimensional space Rn. That is, for all vectors x and y in n-dimensional space Rn, norm of x plus y is less than or equal to norm x plus norm y. And we simply can prove it by considering norm of x plus y and its square to be the inner product of x plus y with itself. Now using the symmetricity and bilinearity, we get it as inner product of x with itself plus 2 times inner product of x and y plus inner product of y with itself. And using the Cauchy-Schwarz inequality, we get it as less than or equal to norm x square plus 2 times norm x norm y plus norm y square. That is norm x plus norm y whole square, which implies our required result. Norm of x plus y is less than or equal to norm x plus norm y. And this triangle inequality in fact helps us to conclude that d of x and g is less equal to d of xy plus d of yz for all x, y and g in Rn, where d is the distance function. So let's try to prove this. First of all, let us consider d of x and y is norm of x minus y. In fact, that is equal to square root of summation xi minus yi whole square for I is from 1 to n. Now for all x, y and g in Rn, x minus y is equal to x minus g plus g minus y, which implies norm of x minus y is less than or equal to norm of x minus g plus norm of g minus y. And this result is due to the triangle inequality for vectors. And that is d of x and y is less than or equal to d of xg plus d of zy for all x, y and g in Rn. And that's how triangle inequality for vectors gives us the way to show the triangle inequality for distance in n-dimensional space Rn. So the distance between points in n-dimensional space Rn satisfies 1. d of xy is non-negative, and the equality holds if and only if x is equal to y. 2. d of xy is equal to d of yx. And 3. d of xy is less than or equal to d of xg plus d of zy for all x, y and g. And therefore, the space Rn together with the distance function becomes a metric space. And one such example of distance function is d of xy is equal to norm of x minus y, which is defined as square root of summation of xi minus yi whole square for i's from 1 to n. And with respect to this distance function, the unit ball in R2 is the circle of radius 1, and you can check it. And further generalizing this distance function, we get some other metrics which are defined as dkxy like this. And corresponding to these metrics, the unit balls in R2 are here. And you can simply visualize that more the value of k, the unit ball is more likely the square of unit length. And from here, you can think something about the metric d infinite. And that's how geometric intuition in Euclidean space can carry you a long way in real analysis, especially in being able to forecast whether a given statement is true or not. And before saying goodbye, we must say, your geometric intuition will grow with experience and contemplation. And maybe here you have just begun to shape your imagination.